Hello and welcome back to another math video. In today's video we're going to be talking about a simple way to factor quadratics. So what exactly is a quadratic? A quadratic is a special type of polynomial with degree 2. And what does that mean? It sounds abstract and to most people it's nonsensical. So let's look at the mathematical equivalent of that statement, which is going to be ax squared plus bx plus c. So the degree of a polynomial is based on these exponents of the variables of x. So here we see the exponent for ax squared is 2. So that means we have a second degree variable right here. And we classify polynomials based on the degree of the leading term. So here ax squared is the largest or the highest degree term, which means it's the leading term. A can't equal 0, otherwise it wouldn't be a quadratic, and B and C can equal 0. They don't always equal 0, but there are some cases where they do. And essentially what that means is that we can have an equation where this is possible. Ax squared equals 0, or ax squared plus bx equals 0, or ax squared plus c equals 0. Now, let's go ahead and talk about some of the special properties of quadratics. So since we have a second degree problem here, that means we're going to have two different solutions for x. So we're going to have an x1 and we're going to have an x2. If we had a third degree, so for example, let's say we had plus dx to the third, then we would have another solution. In this case though, this is a second degree polynomial, or again a quadratic, so it has two solutions. Sometimes we refer to these solutions as the roots of the quadratic. Or just the solutions. So let's go ahead and look at one of the most simple ways to solve these roots. We're going to look at a couple of different examples and really the same method but modified to fit each of these examples. This is the most simple way to solve for the roots, and also really I think in most classrooms this is going to be the first method that's taught. So let's go ahead and look at the quadratic x squared plus 5x plus 6 is equal to 0. So the first thing I'm going to do here is I'm going to go ahead and list each of my constant terms. A, B, and C are considered constant terms. So A is equal to 1 because 1 times x squared is simply x squared. So we exclude writing 1 just for simplicity. B is equal to 5 and C is equal to 6. So in this problem, or in this method of solving for the roots, what we do is we take a large x, and in the top we look at what a times c is, and in the bottom we look at what b is. So here a times c is 6 and b is simply 5. Now what we want to do is we want to come up with a number here and here that's going to multiply to 6 but add to 5. So let's go ahead and look at an example of what that means. So we want a number, or we want two numbers that multiply to 6 but add to 5. And here, oh my bad, but add to 5, not multiply again. So here I'm just using f and g to represent these two numbers. This isn't really conventional, but I thought it would be good to look at these like this as well. Now if you've done any algebra at all, you would know that we can divide out the g on the top or the f on the top to get something like 6 over g, and on the bottom we could also probably do something like f is equal to 5 minus g. But the issue is if we try to do a solution like this, we're just going to end up creating the same quadratic again. So we have to solve these values a different way. And one of the simplest ways to do that is to just break down these numbers into their multiplicative and additive pairs. So 6 breaks down into its multiplicative pairs, again based on what operation we're doing here and here. Or actually, let's go ahead and color that so it's a little more apparent. So these operations are going to determine if we're looking at the multiplicative pairs or the additive pairs. And what is a multiplicative pair? Well, it's two numbers that are going to multiply to 6. In this case, 6 times 1 or 3 times 2. These are 6's multiplicative pairs. We're only going to look at the positive numbers here since we don't have any negative numbers in our original quadratic, so we're just going to leave that out. Now, we do the same with 5, and we're looking for its additive pairs. So the two numbers that add to 5, well, we can start with 0 and 5, then we can do 4 and 1, and then we can do 3 and 2. And what we're doing is we're looking for the pairs that are the same in the additive pairs and the multiplicative pairs. So in this case, 3 times 2 and 3 plus 2 are going to be our solutions. So, oh, I lost my color. So f is equal to 3 and g is equal to 2. Now we're just going to go ahead and check. So f times g is 3 times 2, which is 6, and f plus g is 3 plus 2, which is 5. So those are the numbers that we need. So up here, we're going to put 3 and we're going to put 2. So now that we have those numbers, what we can do is we can break this quadratic into two binomials, which I know is going to sound a little weird, but trust me. So what we can do is take parentheses x plus 3 and then parentheses x plus 2, and we're going to set this equal to 0 still. So this, I'm not exactly sure where this comes from. It's just a form of factoring that we can see. So if we were to FOIL this out, which means we're just going to multiply x to x, x to 2, and 3 to x, and 3 to 2, we still get our original quadratic. So let's do that real quick just to check. So x times x is x squared. X times 2 is 2x. 3 times x is 3x. And 3 times 2 is 6. So this gives us our original x squared plus 5x plus 6 is still equal to 0. What I'd imagine here is we're taking these numbers, 3 and 2, and we're using them to solve by grouping, which we're going to look at later in this video also. But for now, just know that we're going to take the two numbers that we solved for, f and g over here, and we're just going to take x plus f and x plus g and multiply these two binomials to each other. So now that we have these, we can do a nice little property called the zero product rule. And what that means is, since we're multiplying these two binomials together, when one of these binomials is equal to 0, the whole equation becomes equal to 0. Let me fix that equal sign. So if x plus 3 is 0, then it doesn't matter what this x value is because it's also going to be 0 after we multiply. So what we do is we separate these binomials into the left and the right, the two binomials we have, and we set both of them equal to 0. So we're going to take x plus 3, set this equal to 0, and we're going to take x plus 2 and set this equal to 0. So now we're finding the roots. So here, x plus 3 is the same as x is equal to negative 3. So we're just going to subtract. We're just going to subtract 3 from both sides. So this is our first root. So we're going to put a little 1 subscript there. Then for our second root, same thing, we're just subtracting this across, and we get x is equal to negative 2. So now we know the roots for this quadratic. So when x is equal to negative 3, or when x is equal to negative 2, our quadratic will become 0. And we can plug these numbers in to check that. So again, we have x squared plus 5x plus 6 is equal to 0. So we're just going to plug in these numbers. So negative 3 squared plus 5 times negative 3 plus 6 is equal to 0. So negative 3 squared is 9. 5 times negative 3 is negative 15. And 6 is just 6. So here we have 9 plus 6, which is 15, minus 15, which is 0, which means this root works and it's correct. Then we're going to try the other one. So here we're going to take negative 2 squared plus 5 times negative 2 plus 6 is equal to 0. Negative 2 squared is 4, and negative 2 times 5 is negative 10, plus 6 is equal to 0. Again, 4 plus 6 is 10, minus 10 is 0. So this is how we check for our two answers, just to make sure that they are correct. Now let's go ahead and move on to another quadratic problem. So here, we're going to take x squared, let's make that a little bigger, x squared plus 2x minus 8 is equal to 0. Again, what we're going to do is we're going to do this x method. So a times c is just negative 8. Let's make that a little nicer. Okay. And b is just 2. So again, we're going to look for two numbers that multiply to negative 8, and we're going to look for two numbers that add to 2. So let's go ahead and start looking at the multiplicative pairs of f and g, or negative 8. So negative 8 can be equal to negative 8 and 1, can be equal to negative 1 and 8. It can be equal to 4 times negative 2, can be equal to negative 4 times 2, and so on. So here what we notice is we can swap the negative signs to both sides, but since this is a positive number here for f plus g, we know that the larger number is going to be positive and the smaller number is going to be negative. And again, let's go ahead and look at the multiplicative pairs of 2, or the additive pairs, sorry. The additive pairs of 2, which is just 2 plus 0, or 1 plus 1. This one's a little bit different from the last ones. So what we need to consider for this one also, since we have this right here, we need to consider that. So 4 minus 2 as well. I know it seems a little confusing, but since we know that 4 minus 2 is going to be equal to 2, we have to include that in the additive pairs. So when we start having negative numbers, then we have to start going outside of the realm that we're normally used to when we only have two positive numbers. So here, in the previous problem, again, we didn't need to do that because these were both positive, but since a times c is going to be negative 8, we need to include these negative numbers over here. So our two numbers are going to be 4 and negative 2. So these type of problems are slightly harder than the first ones, just because you have to be aware that we're going to go outside of the realm of just what adds to 2 with two positive numbers, because we have to include these negatives as well. So now let's go ahead and do the same steps that we did before. So we're going to take this parenthesis, we're going to do x plus 4, can take another parenthesis multiplying the 2, and x minus 2. So now we have our two binomials. X plus 4 is equal to 0, and x minus 2 is also equal to 0. Now we're just going to solve these. Again, this is the zero product rule, or the ZPR. I don't think most algebra classes are going to require that you know that, but that's what allows us to do this. So now x1 is going to be equal to negative 4, and x2 is going to be equal to 2. Just like that. And those are our roots for this quadratic. And again, we can plug them in just to make sure. So let's go ahead and do x squared plus 2x minus 8 is equal to 0. So negative 4 squared plus 2 times negative 4 minus 8 is equal to 0. Negative 4 times negative 4 is simply positive 16. Negative 4 times 2 is going to be negative 8 and negative 8. So we're going to group together these negative numbers, and we're going to get 16 minus 16 is equal to 0, which shows that that's true. And then let's go ahead and look at the other root also. So here we're going to take 2 squared, 2 squared plus 2 times 2 minus 8 is equal to 0. So 2 squared is 4, 2 times 2 is 4, and negative 8, which is going to be equal to 0. So 8 minus 8 is equal to 0, which shows that's also correct. So that's how you would deal with a quadratic that also has a negative number for one of its terms. Now let's go ahead and look at another example. So we're going to look at the example x squared minus 9 is equal to 0. And what we can do here, we kind of have two different options to go about this one. And they're both good, they're both correct. What we can do simply is know how to FOIL and kind of know how to go into a binomial and out of a binomial and into a quadratic with those binomials. So if we know how to go easily, we know this is one of the rules where we have x plus 3 and x minus 3. And when we FOIL this, we can see x times x is x squared, x times negative 3 is negative 3x, 3 times x is positive 3x, and 3 minus 3 is negative 9. So this is one of those ones that you'll get really comfortable with in an algebra class, and you'll be exposed to this a lot. This might be I think they call it a perfect square. So then this is 0x minus 9, which is still equal to 0. All of these are still equal to 0. So we're left with squared minus 9 equals 0. And now we can do the zero product rule. And we can take x plus 3 is equal to 0, and x minus 3 is equal to 0. So x1 is equal to negative 3, and x2 is going to be equal to 3. So that's the first way that we can go ahead and solve this problem. But there's another one also. So we can go ahead and do it how we normally would. So, yeah. So we have x squared minus 9. What we're going to do is a times c on the top and b on the bottom, which here it's just 0. And then what two numbers multiply to negative 9 and add to 0. So obviously this is going to be negative 3 and 3. Because these are also the same, they're going to add to 0. And then that gets us back to the starting point, where now we can use these binomials to solve the problem. There is actually one more way that we can do this though. So we are going to take x squared minus 9 is equal to 0 one more time, and we're going to move the 9 to the other side. So x squared is equal to 9, then x is equal to the square root of 9, which gives us x is equal to plus or minus 3. So x1 is equal to 3, x2 is equal to negative 3. Be careful with this though, because a lot of people, and me included when I was learning this, what I wanted to do then was, well, if I can do that, what I should be able to do also is take something like this, and I don't even know how pretty of an equation this is just off the top of my head. What I wanted to do though, when I was learning this, is move things over like this, factor, and then set both of these equal to 6. But since we don't have the zero product rule here, we can't do that. That's pretty much it for that problem. So yes, again, we have these 3 different methods that we can use. So we can know our perfect squares and know how to go from a quadratic to a binomial based on those perfect squares. We can do our original x method again, or we can move the 9 over and take the square root. Now let's go ahead and look at some problems where we actually have an a value. So we're going to look at the problem 3x squared plus 9x minus 12 is equal to 0. And so these problems actually get a little bit more complicated, but again, we're just going to work through it step by step. So first thing, we're going to identify what our a is, which is 3, what our b is, which is 9, and what our c is, which is negative 12. So now we're going to do the same x setup, and we know a times c, which is going to be negative 36 on the top, and 9 on the bottom. Again, we're going to solve for f times g is negative 36, and f plus g is going to be 9. So in this case, we're going to take negative 36 and look at all the multiplicative pairs. So we have negative 36 and 1. We have 18 and 2. And we have 12 and 3. So here, 12 and 3 can also be used, if we switch around the 3 to being negative, to get 9. So that's going to be our answer. Another good thing to do with these when they're negative is simply look at each problem and ask yourself, if I put the negative on 3 or 12, could I get 9 out of it? And in this case you can. So that works pretty good. The last multiplicative pair would be 6 and 6. I think 9 is also in there, right? 9 times 4. Yeah, my bad. 9 times 4 is also in there. So we're looking at all of these, and we're just asking ourselves, which of these is going to add to 9? So can't be that one, can't be that one, can't be that one, can't be that one. So we're left with 12 and 3. We're going to make that 3 negative, since this is positive 9 and not negative 9. And so we know f is equal to 12, and g is equal to negative 3. Now we're going to fill this like we normally would, but instead of breaking this into a binomial, what we're actually going to do is break this middle term up based on these two numbers that we got here. And so we're going to take 3x squared plus 12x minus 3x minus 12 is equal to 0. And again, 12 minus 3 is 9. So all we're doing is changing this middle term to fit based on these numbers that we calculated over here. Now what we can do is called grouping. So essentially we're going to take some of these terms that go together, and we're going to simplify them based on that. In this one, it's kind of hard to tell which ones go together, but in the problem that I show you after this one, it'll be a lot easier. So here we're going to take 3x squared and 12x, and we're going to group these together, and then we're going to take negative 3x and negative 12, and we're going to group those together. So now we're just going to pull out the largest common factor from each of these, the greatest common factor. So we have 3x from the first one, which is going to give us x plus 4. And then for the second one, we have negative 3, which is going to give us x plus 4. And now what we can do, since these both have a common binomial that they're being multiplied to, is we can actually factor these out. So we're going to take 3x times x plus 4 minus 3 times x plus 4, and we're just going to make these a common term that they're being multiplied to by factoring both of these out. So we end up with x plus 4 times 3x minus 3. So that's just a factoring trick. And again, if we were to multiply this in, we could do this binomial times this term, and this binomial times this term, to get 3x times x plus 4 minus 3 times x plus 4, times. So we can do it that way, or again, if we wanted to multiply each term, if we wanted to FOIL each term, we could do that as well. So x plus 4 times 3x minus 3. Here, x times x is going to be, x times 3x is going to be 3x squared. X times negative 3 is negative 3x. 4 times 3x is going to be 12x. 12x, and then 4 times 3 is going to be negative 12. And again, that is our original equation that we had up there as well. Since this simplifies to 3x squared plus 9x minus 12 is equal to 0. So we went ahead and proved that these two binomials being multiplied to each other is still our original quadratic. So now let's go ahead and take our two new binomials, x plus 4 times 3x minus 3 is equal to 0. And again, we're going to use our zero product rule, which means we can take x plus 4 and set that equal to 0, and we can take 3x minus 3 and set that equal to 0 as well. So our first term, or our first root, is going to be negative 4, and our second root, add 3 to both sides, so we have 3x is equal to 3, and then divide by 3 on both sides, so that x is equal to 1. So our second root is 1. So these are the two roots for a binomial, a quadratic, which has an a component. On some of these, there actually is a lot easier of a way to do this though, and I'm going to show you that now. So if a can divide b and c, then it's much simpler simply to divide a out to the other terms. So if we have 3x squared plus 9x minus 12, we're going to come over here, 3x squared plus 9x, sorry I forgot the sign on that, plus 9x minus 12 is equal to 0. So we can take this 3 and divide each term by this 3, so that we get x squared, and again this would be a 1 in the front, but we don't care, so we're not going to show it, plus 3x minus 4 is equal to 0. And now we've transformed this quadratic into one that we're much more comfortable with, and one that we could probably solve a little quicker as well. So we're going to do the x method, again, a times c, which is negative 4, and b on the bottom. So what multiplies to negative 4, but adds to 3. So f times g is going to be negative 4. F plus g is going to be 3. So let's go ahead and look at the values that can multiply to negative 4. So here we have negative, let's just make it 4 and 1, where the negative could be on either of them. We have 2 and 2 again, where the negative could be on either of them, and that's all of our options. So which of these is going to add to 3? Well, it's going to be 4 and negative 1. So we know f is going to be equal to 4, g is going to be equal to negative 1. Now we can plug these back in up here, and we can separate our quadratic into a binomial based on these values. So again, x plus 4 times x minus 1. So I think what I was saying earlier in the video, where I wasn't quite sure where these binomials came from, I think these binomials simply come from doing all of this, but typically when we're teaching quadratics that don't have an a value, or where the a value is 1, I should say, we just show this without all the mess of getting to there. But I think if we wanted to do it properly, what we would do is we would take x squared, and then we would break up this middle term again into these values that we found. So 3x becomes plus 4x minus x minus 4 is equal to 0, and then we would group. So in this case, 4 goes with 4 and x goes with x. So here it matters which terms we group with. I think in the last one we could have grouped either of them and it would have been fine, but for every other problem it's going to matter. So here we have x squared minus x plus 4x minus 4 is equal to 0. Again, we can factor out an x here. Start adding some color just to make it a little easier. Oop, and then I forget to add color. Okay. Plus 4x minus 1, and this is going to be equal to 0. So again, what we're going to do is factor out these common binomials. So both of these binomials are the same on both sides. So we end up with x plus 4 times x minus 1. And just for the sake of going over it again and showing you how to do that one more time, we have x times x minus 1, changing colors, x minus 1 plus 4 times x minus 1, which is going to be equal to 0. And what we do is we're going to put a big parenthesis on the outside here, and we have x times x minus 1 plus 4 times x minus 1. I'm not very good at switching the colors here, I'm going to be honest, but it's okay. We'll keep trying. And we're going to make the parentheses about the same size. So now what we can do is group these together. So this is really the same as pulling these all the way out to here. So we end up with x plus 4 on the inside, and then we end up with x minus 1 on the outside. So now that we have these two binomials and they're multiplying each other, we can use the zero product rule. That's an important key aspect of the zero product rule. They have to be multiplying each other, can't add them. That's why we have to do this extra step of factoring out the common binomial here in order to get that. So now we're left with x plus 4 is equal to 0 and x minus 1 is equal to 0. So that x is equal to negative 4 and our second root is going to be 1. So again, these are the same values that we got over here, but it's a different approach to doing it. And obviously I made it a little bit more complicated because I wanted to show where this came from instead of just saying, here, memorize this. But either way, it's going to give you the same answer, and that's the important thing. Now we're going to look at one final problem for this episode, or this video. I know this video is running rather long, but there's a lot of aspects to this and a lot of ways that people can get confused, and I just want to make sure to go over these and go in depth for the different little details that teachers might not explain to hopefully help you guys understand it. So now let's go ahead and look at the next problem. So here we have 3x squared minus 2x plus 8 is equal to 0. I believe, yeah, okay. Just had to make sure that wasn't the same problem. So now what we can do, again, we can do the factoring method with a times c on the top, and we get 24, and we have negative 2. So then we can go ahead and solve for f times g and f plus g, where this is going to be equal to 24, and this one's going to be equal to 2, or negative 2 rather. Again, we're just going to factor our top term, or we're going to find the multiplicative pairs that multiply to 24. So we have 12 and 2, we have 6 and 4, and 8 and 3, as well as 24 times 1. So here are all the multiplicative pairs that are going to multiply to 24. And I think, no, okay. So here, obviously, the only ones that can have 2 whenever we add them is going to be 6 times 4. And since the 2 is negative, we know that our larger number is going to have to be the negative number. So f plus g still equal to negative 2. F is going to be equal to negative 6. And g is going to be equal to 4. So now we can put these up here as well. So negative 6 and 4. And again, what we can do now is separate our middle term into negative 6x plus 4x plus 8 is equal to 0. So this problem, it's much more apparent which numbers are going to be grouped together, since 3 and 6 are both multiples of 3, and 4 and 8 are both multiples of 2, or even 4. So we're going to group together those numbers based on that key insight. Oh, again, I lost my color. I seem to do that a lot. Okay. So we have 3x squared minus 6x plus 4x plus 8. Yeah, plus 8. Which is going to give us 0 in the end. Again, we're going to pull out the greatest common factors. In this case, we're going to pull out 3x we're going to be left with x minus 2. I think we might have done something wrong here. This one, so whenever we pull out the 4 on the other side, we'd end up with just x plus 2 and not x minus 2. So there has to be something which we did slightly wrong on this one. And this is the 3x minus 2x, 3x squared minus 2x plus 8. So let's see what we did wrong, and if it's actually solvable in the way that I was hoping that it is. So, well, that is unfortunate because I did something slightly wrong there. I think it's supposed to be -8 here as well. I think I might have messed that up. Sorry, folks. Sorry for the little mistake there. That is math, though. You make a lot of mistakes in math, and sometimes you just have to accept it, figure it out, and move on. So, there we go. That should work now. So now we have plus 4 times x minus 2, which is going to be equal to 0. So it's really important, I guess that's a good showcase there, it's really important that these values match. These binomials have to be the same in order for us to factor both of them out. If they're not the same, we're not allowed to factor them. So now we can factor like we have been, so we get 3x plus 4, and we get x minus 2. And this is equal to 0, and now we're allowed to use our zero product rule. So we can set 3x plus 4 equal to 0, and we can set x minus 2 equal to 0 as well. So 3x minus 4, we're going to move this 4 over to both sides and then divide by 3. So we have 3x is equal to -4, and we have x, or our first root, is equal to -4 over 3. And now on the other one, this one's much more simple. We can just add the 2 across and get x2, or our second root, is equal to 2. So those are our two solutions to that quadratic, or our two roots to that quadratic. Now what happens if we try to divide out a like we have been, or like I showed you on the last one, since that seems to be a little bit more simple. So let's try on this one as well. So we're going to divide 3 from all the terms. So we end up with, let's move this over a little more, x squared minus 2 over 3 x minus 8 over 3. And this is equal to 0. So you can still do the same process here as we have been. So we have -8 over 3, and we have -2 over 3 as well. That would make sense also, since -24 has to, or since 24 has to be negative. Yep, okay. So here we can do the same sort of process. We have f times g needs to be -8 over 3, and f plus g needs to be -2 over 3. So what values multiply to -8 over 3, and what values add to -2 over 3? So unless you're comfortable with fractions, this method becomes a little bit grosser to do if you can't divide out your a term evenly. And so then you would have to do this grouping method to figure out your answer. If you are comfortable with fractions though, um, obviously there are ways to figure this out, and it's not too bad. So yeah, I'm just gonna leave it at that. I'm not gonna finish this one this way. But basically, that is a not so concise introduction to factoring. So let's go ahead and run through everything again. So again, a quadratic is a polynomial that has degree 2, or a term that is squared. Here we introduce the x method of figuring these out. So the x method where f times g is a times c, and f plus g is b, or in this case 6 and 5. So f times g is 6, f plus g is 5. Then we introduced the idea of breaking our quadratic into binomials based on these numbers. And remember, these binomials come from grouping all of the values together. We showed how to use the zero product rule to then set both of these equal to 0 and solve for both of our roots. And again, based on what the degree is of our polynomial, that is going to be how many roots we have. So since quadratics are second degree, they're always going to have 2 answers. Here we introduced what happens when we have a negative, grouping these values together, the multiplicative and additive pairs, and how that can change a little bit, how you have to go outside of the realm of positive numbers and figure it out. So whenever we have negative numbers, it becomes a lot more intuitive and a lot more simple to focus on the multiplicative pairs and then compare that to our additive number to come up with a pair for both of them. It's a much simpler process to do it that way. Here we introduced perfect squares and how there's many different ways of solving these. We looked at 3 of them just right here. And you can't really do the move the constant to the other side whenever we have a b term, since that kind of messes up our whole zero product rule property that we've developed. Then we looked at what happens when we have an a term, multiplying that times c to get this over here, and then figuring it out like how we normally would. Then we would plug these in, so we separate this middle term into these numbers based on our solutions over here. Then we factor out the common binomials, set it equal to 0 again, and use our zero product rule. Our zero product rule really seems to be carrying in this video, and it is a very useful rule to know. Although, when you learn this in algebra, your teacher's not really going to tell you that. They just say, set it equal to 0. But there is like a rule and niceness to it also. Again, we're looking at if a is not equal to 1, and dividing. If all the terms are nice, we can just divide and do it that way. It's much simpler. But if they're not nice, then we have to do it this way. And realistically, we don't have to, but we end up with fractions, which probably makes it more complicated in the long run. And so I think it's better to just not do it that way. I think it's better just to do it this way for now with the tools that we have. In the future, you might want to come back and complete the square or do something like that to this problem, and it might be a little bit easier. But for now, it's just easier to take the common binomials and do all the grouping methods as well. Anyways, that is this video. I know it was long, I know it was arduous to get through, but there's a lot of nuances and a lot of ways that you can go wrong, so hopefully if you're stuck learning this or you want to go through and learn some more ideas of grouping and where our binomials come from here, I hope you enjoyed this video. And thank you so much for watching. If you made it to the end, I ask you to leave a like for all of the math, and maybe consider subscribing to the channel if you're liking these videos. Anyways, let me know what sort of videos you guys would like to see in the future, whether or not this video was helpful, if you'd like to see it shorter or longer. And yeah, thank you guys so much. I'll see you in the next one. Bye.